Hello and welcome. Hypothesis testing ends up being a topic many students rely heavily on memorization. I want to make it easy for you. I want to give you the gist of hypothesis testing. By the end of this video, I hope to achieve one of these things. Oh, I didn't know hypothesis testing was so useful. Or, oh, I didn't know hypothesis testing was so intuitive. Or, I like hypothesis testing. If I manage to achieve any of those things, then I consider that a success. A quick note that the hypothesis testing procedure I'm going to use in this video is not in the syllabus. Don't focus on the nitty-gritty. Focus on how hypothesis testing can actually help you come to a decision using statistics. So let's get started. The story goes like this. You have a friend who's pretty sus. He comes up to you and say, hey, if you give me a fair coin, I have a special technique. When I flip the coin, heads will come up more often than tails. So skeptically you say, well, do it 20 times. As the friend is flipping the coin, a few thoughts are going through your head. And if this guy has no technique, we are expecting to see about 10 heads and 10 tails. But what if this guy comes up with, say, 11 heads? What conclusion will you come up with? Will you say that, oh, 11 is really near to 10. Just one more. Probably got lucky. I still don't believe that he has some special technique. Or do you go like, wow, you got some math skills, bro. 11 out of 20, that's more than half of the time. And what if the number of heads was 17? Will you still say that, oh, 17 is just 7 more than 10. He got lucky. Or will you say that, wow, he probably has some special technique going on. I'm going to go ahead and guess that you're going to say, for 11, he got lucky. 17, you're gonna say that he got skill. So let me play the devil's advocate here. How about 12? How about 13? 14, 15, 16? At what point do we start switching from he got lucky to math skills, bro? Let's look at how we can model this question statistically. I could let, say, a random variable like x represent the number of heads, and x will follow a binomial distribution. Since we have 20 flips, what should I put here for the chance of getting a hit? 0.5? Or should I put a number that's greater than 0.5? Here's the problem. If I wanted to put a number that's greater than 0.5, what number do I put? 0.6, 0.7? It's hard to nail down a number, and that is why hypothesis tests are always conducted on a fixed number. You recall your null hypothesis and alternate hypothesis? There you go. And the null hypothesis is when a certain parameter is equal to something. If it was more than something, we can't fix down a number, and we therefore cannot conduct the test. Next, you probably need to think about some kind of statistical way to figure out what is the chances of getting 11 hits or 12 hits or 13 hits. For that, we can turn to our graphing calculator, but to make things faster, I'm going to use GeoGebra. So go to geogebra.org, click on Start Calculator. On the drop-down menu on the top here, choose Probability, and under this drop-down menu over here, choose Binomial, and you can key in the parameters, which is 20 trials, and the chance of getting a hit is 0.5. So one of the more meaningful statistics we can actually use is the cumulative probability. Let's look at the probability of flipping 10 hits or less. That's about 59%. But if we consider the converse, which is the probability of flipping 11 hits and above. What are the chances that someone, right, if you ask them to flip the coin 20 times, they get 11 hits or more? That's about 41 or 42%. I wouldn't consider that to be skillful. If you go ahead and do this for, say, 0 to 11 instead of 10, about 75% of the time you will have people flipping 11 hits or less. And the converse of that will be 25% of the time you have people flipping 12 hits or more. 1 in 4% can flip 12 hits or more. So I wouldn't consider 12 to be skillful. So I've gone ahead and tabulated all this information on my iPad. If you focus on this column over here, this tells me that 41% of the time, you're gonna have people flipping 11 hits or more. 25% of the time, 12 hits or more. 13% of the time, 13 hits or more. 6% of the time, 14 hits or more. Then the question naturally becomes, at what percentage do we start to cut off and say that, well, this is skill and it's no longer luck. And there is the notion of significance level. So even before you start the test, even before you look at these numbers, you agree on a significance level and say that, okay, anything that's more rare than, say, 5%, we will consider that as skill. So over here, I've drawn the cutoff line at 5%. If someone were to flip 15 hits or more, that only happens 2% of the time. Well, I'll say that you probably have some skill. Well, it could also be due to luck, but most likely it's due to skill. To wrap things up, let's look at the idea of the test statistic and the critical region. The critical region will be 5% of area under the graph. Remember, we have a cutoff point, this area under the graph. If our friend gets anything in this area, maybe 15 flips, 16 flips, 17 flips, and beyond, he is indeed skillful. This is the idea of the test statistic being in the critical region when we are comfortable enough to reject the null hypothesis. The other way to make a conclusion is to look at the p-value. Recall that to get 15 hits and more, that's about 2.1% of the time. Since if the area under the graph over here for 15 and more is about 0.021, we say that if the p-value is lesser than 0.05, that has the same kind of meaning as the test statistic is inside the critical region, which is why when we say if p-value is less than level of significance, we are comfortable to reject H naught. So I hope you found this intuitive, or you found hypothesis testing to be actually something that is quite useful. In further videos, we'll look at practice questions and also a flowchart on how to do hypothesis testing. And I guess I'll see you there.